Welcome to our channel for probability and statistics. In this video, we will talk about hypothesis testing of the difference of population mean and when their variance unknown but equal. So we know if we want to test two independent random samples to test their population mean difference with hypothesis, and we only know that their variance are equal, but we do not know the exact value of the population variance for both population. So in this case, we get the sample from two independent population and can use so-called pooled t-test, or say two-sample t-test, to test the difference of these two population mean. So we formulate the hypothesis if we want to make a two-sided test. So the hypothesis for H0 or null hypothesis is mu1 equal mu2. So mu1, mu2 are the two population mean respectively. And for the two-sided hypothesis test, H1, or say the alternative hypothesis, is H1 and mu1 not equal to mu2. Then we can get the test statistic from the sample. So the test statistic T from the sample is the sample average difference minus the hypothesis difference between the population mean. For example, if we want to say population mean is larger than population mean 2 with 50, so we just use 50 here. So this is the hypothesis, the population mean difference. And SP in the denominator is the pooled variance from the sample. So this is combined with both variance from sample 1 and sample 2, then pooled with their sample size. Then we have to multiply the square root of their pooled sample size. So this statistic follows a t-distribution with n1 plus n2 minus 2 degrees of freedom. So if for the two-tailed test, if we in the end get the t value in this side or in this side, on one of the red area, so this is the critical area, then we say the test is significant and reject H0 and will in favor of H1. So this is for the two-tailed test. So for example, if we specify the significance level of the test is 0.50, 0 is 0.05, then both area will have 0.025 for the probability. But for the one-tailed test, the H1 or alternative hypothesis is like mu1 minus mu2 larger than d0. Or we just mu1 minus mu2 less than minus d0, for example. So not both, but for the two-tailed test, the test statistic can be located in both ends, but for the one-tailed test, it's only possible in one end. So we will show later with examples. So for example, an experiment was performed to compare the abrasive wear of two different laminated materials, and 12 pieces of material 1 were tested by exposing each place to a machine measuring wear. 10 pieces of material 2 were simply tested. So the sample size for for the population 1 is 12, and the sample size for population 2 is 10. And in each case, the depth of wear was observed. The samples of material 1 given the average. So sample 1 average, the wear of 85 units with a sample standard deviation 4. So this is S1, standard deviation for the sample size 1. And the sample of material 2 give an average of 81 with a sample standard deviation of 5. So the sample average for the population 2 is 81. And standard deviation for the second sample is 5. So the question is, can we conclude at the 0.05 level of significance that the abrasive wear of material 1 exceeds that of material 2 by more than 2 units? Assume the population to be approximately normal with equal variance. So this question assume the equal variance from a normally distributed population 1 and population 2. So this matches the requirements of our test formulation in previous pages. And the hypothesis like this question is a one-sided test, because we want to test if one population is better than the second population by more than 2 units. So this is the assumption that we know 1 is better than 2, but we are not sure it's more than 2 units, right? So we exclude the probability that material 1 not less than material 2. We are not interested in this case. We're only interested in and focus on the hypothesis that material 1 if is more than 2 units than material 2, right? So this is a one-side test. And one-side test, this alpha level will be put in only one side. So if we take a look at this, so alpha will be here, not half alpha. For one-side test, all the alpha 0.05 will be located in this blue area, right? So the solution is we let mu1 and mu2 represent the population means of the abrasive wear for material 1 and material 2. Then we formulate H0, null hypothesis is mu1 minus mu2 equals 2, right? And alternative hypothesis is mu1 minus mu2 larger than 2. And we define alpha is 0.05. So from this sample, the critical region, this is the critical region, and T alpha is critical value. So from the sample, because this t-statistic follows a t-distribution of 20 degrees of freedom, because the sample size 1 is 12 and 10, second is 10, right? So 12 plus 10 minus 2 is 20. And for the t-distribution 20, critical value 0.05, this value is 1.725. So we first from t-distribution find the critical value 1.725 under 20 degrees of freedom. Then we will calculate to put in all the information in this formula. So x1 bar, s1, n1, x2 bar, s2, n2 all can be found from the problem information. Then we calculate the pooled standard deviation of the sample, 4.478. Then we can calculate the t-statistic from the sample, is 1.04. So, because the critical value is 1.725, so 1.05 is on the left side in the white area in this t-distribution, right? So it's not in the critical region. Critical region is larger than 1.725. And we can also say the probability of t larger than 1.04 is about 0.16. So the sample t is look like stay here, 1.04, right? So if we take a vertical line, so this area will much larger than alpha, right? Alpha is only 0.05. So here is 0.16, almost like here. So the rejection is the significance is not the significance of this test, right? So we do not reject edge 0. So from the sample, we are unable to conclude that the abrasive wear of material 1 exceeds that of material 2 by more than 2 units. So we have to be cautious about the conclusion. The conclusion is not to reject edge 0, and we cannot conclude that the material 1 is larger than material 2 by more than 2 units. So this is the conclusion. Thanks for watching.